Alright, Math 3, here is our benchmark test review about polynomials. So everything we've covered with polynomials, and if you know how to do all these problems, should be good to go on that benchmark. So make sure you study up and you're all ready to go. So, first things first, we are going to do subtraction. So with addition and subtraction, it's just combining like terms. What I like to do when I have a subtraction like that, I like to make it a plus, and then apply the negative to everything after it. So that'd be a negative 5 plus 3a squared plus, minus 6a to the 4th. So then I look to combine like terms. So 3 plus 4a to the 4th minus 3a squared. And usually you like to do the highest degree, so I've got positive 4a to the 4th, negative 6a to the 4th, so that would be negative 2a to the 4th. Okay, then we've got negative 3a squared, positive 3a squared, so that would become 0a squared, or just 0. And then 3 minus 5 would give us negative 2. So there's our answer for the first one. Second one, same idea, so I get 5x to the 4th minus 7x plus 7x squared. Then minus 7x minus 2x squared as we apply that negative to everything, plus 5x to the 4th. So 5x, 5x, so we get 10x to the 4th. Then positive 7 minus 2x squared plus 5x squared. Then negative 7x, negative 7x, negative 14x. When it's addition, we just start combining like terms. So 7 minus 8 would be a negative x to the 4th, or negative 1. 5x cubed, 7x cubed, plus 12x cubed. 1 and 8, plus 9. And the last addition one, we would go with squared first, negative and negative. Would give us negative 9n squared. Then 3n minus 8n would be negative 5n. Then 4 and 1 would give us a positive 5. Alright, now on products, okay, a few different ways we can do these. You can do the FOIL method, which, where you just go 5v times 3v, you get 15v squared. Then 5v times 1, positive 5v. Negative 1 times 3v, negative 3v, negative 1 times positive 1, negative 1. And then plus 5v minus 3v, we combine like terms to be plus 2v. And scoot that minus 1 closer, and we get it that way. Okay. The other way we can deal with this is by using that area model, okay, which can be useful the more terms we get. So r squared, 8r, and 3, 4r, negative 6, 4r times r squared would be 4r cubed, r squared and negative 6, negative 6r squared, 4 and 8, 32, r and r squared, oh, that should be r cubed, huh? Negative 6 and 8, negative 48r, 4 and 3, 12r, negative 6 and 3, negative 18. Then combine like terms, so I get 4r cubed. Then negative 6 and positive 32 would be a positive 26r squared. Negative 48, positive 12 would be a negative 36r. And then minus 18. Okay, and that works the same way. Regardless of how many terms you get, you can just keep creating boxes that are big enough. So 7b squared, 7b and 3, 7b squared, negative 2b, negative 1. So we'd get 49b to the 4th here, 49b cubed, and 21b squared. Then negative 14b cubed, negative 14b, and negative 6b, b squared here. Negative 7b squared, negative 7b, and negative 3. Combining like terms, so 49b to the 4th Then we got the cubes. 49 minus 14 would be 39. 35 plus 35b cubed. Then the squareds. 21 minus 14 would be 7. Minus 7 would actually eliminate it. So we get rid of those ones. Negative 6, negative 7, minus 13b. And then finally, minus 3. Clear some space here. Okay. Last multiplication, same idea. Another 3 by 3. 4k squared, positive k, negative 4. 7k squared, negative 4k, negative 1. So 28k to the 4th, 7k to the 3rd, negative 28k squared, negative 16k to the 3rd, negative 4k squared, positive 16k, negative 4k squared, negative k, positive 4. So we get 28k to the 4th. Then 7 and negative 16 would be a negative 9k cubed. Then negative 28 minus 4 would be negative 32, then negative 36. So negative 36k squared. 16 minus k would be 15k. And then finally plus 4. Alright, so there's those guys. Alright, now if you remember, we talked about these remainders, okay? Now we don't want to actually divide the polynomial by the factor, okay? That's not the easiest way to do it. What we find out is when we do that, the remainder is simply the y value given this x value. So this x value of negative 1, what's the y value? Okay, so one way we can do this is we can graph it and look at the x value of negative 1 and then see what that y value is, okay? So there's that option, and in some cases that'll be the best one to do. We'll take a look at that one maybe on number 12. I'll show you that one to you last. Let's just see how we do them by hand, since it's easier for me to work these ones out than try to graph. But I will show you a graphing one, which you can do on a graphing calculator or Desmos. So I just plug in my x value for x, so I get 3 times negative 1 cubed minus 4 times negative 1 squared minus 9 times negative 1 plus 5. So negative 1 cubed is negative 1 times 3 is negative 3. Negative 1 squared is positive 1 minus 4. Negative 9 times negative 1, positive 9 plus 5. Negative 3 minus 4, negative 7 plus 9, positive 2 plus 5. We get a remainder of 7. So pulling up the graph, as we can see, when we, normally if I could show you exactly on the graph, when we go to negative 1, we get to 7. That's what the remainder theorem tells us, that if we divide into it, whatever that remainder is, that is the y value. Okay? So you can do it either way. You don't have to do it both. I'm doing it both just to show you. Decided to do both. So we've got a negative 7 here, because we always do the opposite. So I do negative 7 to the 5th plus 6 times negative 7 to the 4th minus 6 times negative 7 cubed plus 4 times negative 7 squared minus 29 times negative 7 minus 47. Okay. Easiest way in the calculator is just to take those numbers and just multiply them out. Instead of doing them a piece at a time, that's going to be probably the easiest way to do this. So when we multiply those powers out, this is what we get. And then we add and subtract these, and we get, and once we do all those, by the way, that should be plus, not minus, we get 9. So the point, negative 7, 9. So if we graph it, we can see that same thing. So if I graph this, looks like it should be the x-intercept, but it's not, because these are such big numbers. But we get x value of negative 7, y value of 9. So it works doing it either way. Alright, so if we look at 11, Okay, positive 1. So 6 times 1 cubed minus 4 times 1 squared plus 2 times 1 plus 6 gives us 6 minus 4 plus 2 plus 6. So 2 plus 2 plus 6 gives us 10. We graph that, and we see x value of 1, y value of 10. Divide that 1 into here, that remainder is the y value. Okay, that remainder theorem tells us that. So then we do this last one. Okay, so a negative 3 here. So I've got negative 3 to the 4th minus 3 times negative 3 cubed minus 12 times negative 3 squared plus 28 times negative 3 plus 39. So we get 81 plus 81, let's see, then minus 3 squared would be 9, so 72, and then minus 28 times 3 would be 60, 70, 84, plus 39, which we add those together and we get, well, that's not right, is it? That should be what, 108? And we get 9. X value of negative 3, y value of 9. Check with our graph, and we see that it works. So whether you want to do it out by hand or just check on your graph, works the same way. And then you don't have to worry about that nonsense of using synthetic division or long division to help you with that. Okay, now, same idea when we're finding roots. Okay, we could factor things and find out what they are and do that by hand. But the easiest thing to do really is just to graph them and go that way. Find where their roots are. Now, the only issue we'll run into is if we have an imaginary one. In that case, then we're going to use our calculator. And you should know how to do that. I don't have the calculator to show you, so I'm not going to do that. I'll just show you on graphs from Desmos, because right now that's all I have access to. I don't have a regular calculator. But you should remember that you go to Calculate, hit Menu, and you go to Algebra, which is 3. Then you go to Polynomial Tools, which is 3. Then find Roots, which is 1. Then you type in all the coefficients, and if it's missing a coefficient, like this one doesn't have an x or a constant, they become zeros. Type it in, and that'll tell you all the roots that you need. Okay? So, as I enter this one in, we can see that power of 3 would tell us that it's a degree of 3 tells us we're going to have 3 roots. So we get 2, 0, negative 2, 0, negative 5, 0. And there's our roots. And we notice, because they're just crossing like they are, we all have a multiplicity of 1. Okay? So you can do it on the graph easy peasy. Or like I said, in the calculator will give you the same results. So we take a look at number 14, a degree of 4, so we should have 4 roots. So we graph it, and we see that there's only 3 right here. So that one, negative 5, 0, has a multiplicity of 1. Negative 1 has a multiplicity of 1, but see how this one, 0, 0, touches? That means it has a multiplicity of 2. So 1, 2, 3, and 4. Okay? And there's our 4 roots right there. You need to make sure that if it has a high or multiplicity, that you put that multiplicity in there. So then we look at 15 with a degree of 6. So we should have 6 roots. So we find our graph. And we find a problem. These only have a multiplicity of 1. And there's only 2 of them. So here's where we have some complex roots with I, which would mean we would need to use the calculator to find those complex roots, which if we did, would look something like this. So if we do it in the calculator, we'd end up with also having 2i and negative 2i, because they always come in pairs. And then negative 2.236i and negative positive 0.236i. Okay? And that would give you all 6 of them. So that's the reason why I say it's a good idea to use just the calculator tool to get those. Okay? 16 has a degree of 4, so when we graph it, we can see that we've got our 4 roots, all 4 of them right here. So Graphing them does a really good job of helping us find them, and they all had a multiplicity of 1 because there was 4. But like I said on number 15, sometimes you need to use a calculator to help you find them. So 17, degree of 3, we should have 3 roots. Let's see if we do on the graph. So we can see we only have 1 real root, and it's only got a multiplicity of 1, so we have 2 imaginary. If you type it in the calculator, you would end up with 4 plus I, and then its negative version, 4 minus I. Okay, and that would be the 3 roots for that one. And you can look those up in your calculator in class to double check that. Okay, then the last one, number 18. Okay, we should have 3 roots here as well. Let's see what we do on the graph. And we have our 3 roots right here, here, and here. Okay, so using technology, you should be able to, as long as you understand what roots and zeros are, should be good to go on those. Okay, now on the next ones, we're going backwards. Now we're given the roots. This time we're going to make the equation. So, remember, we'd started out and it'd be x minus 3, because you do the opposite when you find their factor. Then x plus 3, then x minus 1. Then we multiply to get x squared minus 3x plus 3x minus 9. So those would cancel out, so x squared minus 9 times x minus 1. So we get x cubed minus x squared minus 9x, and then plus 9. And there's our answer. There's our least degree for that one, based off of the roots, which we change into factors, and then we're able to do that. And they call it the least because these could have higher multiplicities, but we're just assuming they don't, and so we do the smallest one we can get. Okay, now in 20, we've got a fraction, so these ones can be a bit trickier. But remember, they're equal to x, so if we try to get the left side to be 0, we'd end up figuring out that it's actually 5x minus 2 is the factor there, and a multiplicity of 3 means we're doing it 3 times. Okay, so if we need to, we can do the area model, giving me 25x squared minus 10x minus 10x plus 4. So I get 25x squared minus 20x plus 4, which that I then have to multiply by the last one, 5x minus 2. So I get 125x cubed minus 100x squared plus 20x minus 50x squared plus 40x minus 8. So I combine like terms and I get 125x cubed minus 150x squared plus 60x plus 8. Alright, now 21 and 22, when we're dealing with radicals and imaginaries, remember we always have the opposite version going on. So I've got x minus 1 minus square root of 7 times x minus 1 plus the square root of 7 times x minus 3 minus the square root of 3 times x minus 3 plus the square root of 3. So these ones, it's often a good idea to use the area model just to help you keep things in track. So x negative 1, negative square root of 7, x negative 1, positive square root of 7. Now, the nice thing about these ones is as you get going, you realize that these roots are going to eliminate themselves. Okay, that's a negative version, that's the positive version. Positive version, negative version. Root times a root gives me just the answer. So, on this the left 2 roots, I get x squared minus 2x, and then 1 minus 7 would be minus 6. Okay, but we are going to have to multiply that by some more pieces. So I do the right side. So x negative 3, negative square root of 3, x negative 3, positive square root of 3. X squared minus 3x minus x root 3, negative 3x positive 9, positive 3 root 3, x root 3, negative 3 root 3, and then negative 3, because the roots undo each other. Those cancel, so we get x squared minus 6x, and then 9 minus 3 would give us 6. Now we can multiply these together to get our answer. X to the 4th minus 2x cubed minus 6x squared, negative 6x cubed, positive 12x squared, positive 36x, 6x squared, negative 12x, negative 36. So my answer, and this is for number 21, becomes x to the 4th. Then negative 6, negative 2 would be negative 8x cubed. Then all my squares, 6 and negative 6 undo each other, so 12x squared, 36 minus 12, 24x minus 36. So quite a bit of work for those ones. Alright, now 22, we have the imaginary. And again, we have to have the positive and negative version, which it looks like they already have. So I've got x minus 2i, x plus 2i, and 3, oh, hold on, we need our x minus 3 plus 2i, and x minus 3 minus 2i. Okay, so again, these i's kind of work like the radicals, and you'll see that they actually undo each other. So I get x squared, negative 3x, 2xi, negative 3x, positive 9, negative 6i, negative 2xi, positive 6i, and then 2 times negative 2 is negative 4, I times I is I squared. So, then we get x squared minus 6x. Those undo each other. X squared, because I is the square root of negative 1. If we square them, just gives us negative 1. So I get negative 4 times negative 1, which is positive 4. 9 plus 4 gives us 13, and that should have been a 13. Okay, so we're going to need to do it one more time because we've got to deal with this left side now. So, this one, same idea. X negative 2i, x positive 2i, so I get x squared minus 2xi plus 2xi, and then again negative 4i squared, so those cancel, and we get x squared plus 4, because negative 1 times negative 4 is a positive 4, so x squared plus 4, so I get x to the 4th minus 6x cubed plus 13x squared plus 4x squared minus 24x, and plus 13 times 4 would be 12, and 40, 52. So for number 22, we get x to the 4th minus 6x cubed plus 17x squared minus 24x plus 52. And that's how we go backwards from having the zeros back to the equations. Okay? Alright, now, general shape of each function. So remember, and behavior is really what we're asking for here. Okay? We have positive, we have negative, we have even and odd. So even degrees with a positive coefficient, both of them go up. Okay, which if we look at 25 and 26, it's just describing it instead of drawing it. So 26 would fit that. So I would either write the limit as x approaches positive infinity. As it goes to the right, my function is going up, which is positive infinity. We can also write it as x approaches infinity. F of x approaches infinity. Okay, and that's the right side. Then we do it for the left side. Limit as x approaches negative infinity of f of x also goes up to positive infinity. So I just change that part to negative infinity and write it again. And you can choose either one to do. Okay? Now, if we have an odd that's positive, the right side goes up, left side goes down. So 24. So it wants me to sketch the general shape. So I'm just going to sketch something like that. right side goes up, left side goes down. Okay, now if we have odd negative, it just flips it. Left side goes up, right side goes down. So sketching that one looks something like this. Okay, and the last one, negative even, they both go down. So I would say as x approaches negative infinity as it goes to the left, f of x approaches negative infinity. And as x approaches positive infinity as it goes to the right, my function f of x goes down, or negative infinity. Okay, and that's dealing with end behavior. Now we've got two problems where we are just talking about their features. Okay, so if I look at this, I can tell the degree is even based on the fact that they're both going up. I've got 1, 0 right there. So zeros, that would be a negative 3, 0 with a multiplicity of 1. Then at negative 1, looks like I have a multiplicity of 3, so negative 1, 0, multiplicity of 3. And then 4, 4, 0, looks like I have a multiplicity of 4. So adding those up, 3 and 4 is 7, and 1 is going to give me 8. Okay, looks like my y-intercept is halfway between, so 0.5. Alright. Now, max and mins, we're going to kind of have to just guess here. I do know one of my minimums. It's 4, 0. Okay, I have another minimum right here, which I would just estimate at negative 2.5 and about negative 0.75. And I have a maximum up here, which I'd estimate at about 2.5, and we'll say 5.5. Okay, so increasing and decreasing. Okay, so we start out decreasing till we hit that minimum. So I'd start out at negative infinity until I hit that minimum of negative 2.5, because I'm only dealing with x values. Then we increase till we hit the maximum. So at negative 2.5 I start increasing until I hit positive 2.5. Okay, then we take a jump, and now we're decreasing till we get to 4. So 2.5 until we get to 4. Then we go back to increasing, and we go from 4 to infinity. Okay, positive and negative. It's really only negative in one small spot. So positive from negative infinity to negative 2.5. Then it takes a jump at negative till negative 1, and it's positive again. So negative 1 to positive infinity. Oops. Okay, negative is just right here. So negative would be from negative 2.5 to negative 1. And behavior, they're both going up. So I'd write as x approaches negative infinity, f of x approaches positive infinity. And as x approaches positive infinity, as it goes to the right, f of x approaches positive infinity. It goes up. Alright, now the last one. And I don't have a ton of time to do it, so let's see if we can get her done. End behavior, left is up, right is down. So limit as x approaches negative infinity of f of x would equal positive infinity. As it goes left, it's going up. Limit as x approaches positive infinity of f of x, it's going down to negative infinity. That would be our end behavior. Okay. Alright, now I'm going to have to do some of this work. I've only got a minute left, and I want to finish this one. So I'll do some of these and then kind of talk about them, and pause and put some answers down. Alright, so zeros, negative 4, 0, multiplicity of 2 because they touch, and 4 multiplicity of 1. So 2, 2, and 1 give us 5. Y-intercept also at 0, 0. For our maximums, 2 here, one that I estimated negative 2.52. The other one I estimated 9.3, close enough, right? And the two minimums are also two of our zeros. So then we're going to use these max and mins to help us with our increasing and decreasing and the x-intercepts for positive and negative. So we look at increasing, we start at decreasing, so negative infinity to positive 4, then increasing negative 4 to negative 2.5, decreasing negative 2.5 to 0, increasing, decreasing, and positive and negative. Is just like that.